Good morning, gentlemen, and happy Monday. Today is May the 18th, and today we're going to talk about section 14.2, which is all about circular orbits. All right. Now, one of the best ways to teach you or talk about circular orbits is to use the concept of the moon's orbit around the Earth. All right, this is a very nearly circular orbit, although not perfectly circular. All right, you may have noticed that at some times you'll see that the moon looks like it's closer to the Earth. It appears bigger in the sky, and that's because it really is. All right, so even the moon's orbit is not perfectly circular, and we'll talk about that some more tomorrow. But to start out with the easiest concept, let's talk about a satellite that is in a perfectly circular orbit. And we'll use the moon as an example, although it's not completely true. So for satellites in circular orbits, their motion is always parallel to the surface of the Earth. So if this is the surface of the Earth, and I'll draw a line here, and notice that that line is tangent to the surface of the Earth. Notice that the moon's velocity or speed is moving in the same direction, parallel to the Earth. And of course, that makes it perpendicular to the pull of gravity. And so the thing is, why doesn't the moon crash into the Earth? And the answer is that for every 5 meters it falls, it also moves 8,000 meters. All right. Now that's a ratio, not an actual number, because the moon is so much further away from the surface of the Earth than, for example, you throwing a baseball. But still, the ratio is the same. Now, for satellites that are close to the Earth, and by close, I mean about 150 kilometers. That's where that high up is about where we put most of our weather satellites, our communication satellites, spy satellites, that sort of thing. And so at about 150 kilometers above the surface of the Earth, the period of a satellite is about 90 minutes. Now, what that means is that every 90 minutes, it only takes an hour and a half, that's not very long at all, for a satellite to actually orbit the Earth. It turns out that the speed of a satellite is actually governed by a few things, including the mass of the Earth and the mass of the satellite, but even more importantly, it's governed by the distance above the Earth that satellite is. At a distance of for example, at the distance the moon is away from the Earth, the period is about 27.3 days, almost a month. All right, almost a month. Now, an example question then to chew on a little bit here. There are usually alternate explanations for things. Is the following explanation valid? Satellites remain in orbit instead of falling to the Earth because they are beyond the main pull of Earth's gravity. True or false? For those of you who said false, you are correct. All right, this is not true. As a matter of fact, according to Newton's law of universal gravitation, it doesn't matter how far apart two objects are in the universe, they will still have a gravitational pull. Okay? And so, therefore, the answer is no, right? They are not beyond the main pull of Earth's gravity, okay? If they were, then they would continue to move in a straight line and wouldn't be pulled in that circular orbit around the Earth, all right? Satellites remain in orbit because they are being pulled by gravity, not because they are beyond it, okay? So think about that. All right, they remain in orbit because they are pulled by gravity, not because they are beyond the pull of gravity. Okay. That leads us to a second question here. Satellites in close circular orbit fall about 5 meters during each second of orbit. How can this be if the satellite does not get closer to the Earth? Well, these same satellites that are falling about 5 meters each second are also traveling about 8,000 meters horizontally. And so, therefore, they are indeed falling, but they're falling around the Earth because the curvature of the Earth is uh, or has a rise of 5 meters over a run of 8,000 meters, right? Think about the slope formula that you learn in your math classes, right? Rise over run. Well, if the rise is 5 meters and the run is 8,000, then you're always going to maintain the same height above the Earth as you rotate around the Earth. Okay? All right, my friends. So that finishes our discussion of section 14.2. Now, just to be very clear, worksheets 13.1 and 13.2 were due on Thursday. All right, if you have not finished those, please make sure you get them in as soon as possible. Worksheet 13.3 is going to be due this evening at, by close of business today. And in addition, I would like you to do review questions 1 through 10 in chapter 13, all right, and submit those either via photograph or by just typing them into an email. Now, listen very carefully because there's one more assignment, the review questions 11 through 20 for chapter 13. The thing is that I want to give you a review activity on Wednesday morning. And so the sooner it's the assignment is not going to be due until Wednesday evening. But if you send it to me beforehand, I can send you the correct answers, and so that you'll do better on the review activity on Wednesday. All right. So even though the 11 through 20 is not going to be due until Wednesday night, if you get it to me before Wednesday morning, like Tuesday, then I can grade it and send you the correct answers so that you have an easier time on Wednesday's review activity. All right. So that's the deal for Monday, May the 18th. Have yourselves a lovely day, and I will see you soon.